Electric motors have been part of the industrial age for over 100 years, with few homes, offices or factories where they're not to be found. Motors are available in many types, in an amazing variety of sizes for every purpose. Here at this water treatment plant, these mighty AC motors are pumping millions of litres of water every hour from wells deep under the Kent countryside.
Although the range of AC motors is vast and most of them work in a similar way, it is the three-phase induction motor which is most commonly used for industrial drives. Indeed, there are more steady-speed induction motors in use than all other types of electric motor put together. That's because of their relative low cost, extreme robustness, reliability and simplicity. Let's start then by looking at the parts that make up a typical three-phase induction motor. With the fan cover, cooling fan and the two end shields removed, we can see that the motor has two main parts: the rotor, which revolves, and the stator frame, which carries the fixed windings which are assembled into insulated slots. We will see later on how these windings produce a changing magnetic field in the stator stack, which causes the rotor to turn. Depending on the intended use of the motor, the frame can be manufactured from sheet steel, rolled and welded, cast iron, or as in this case, cast aluminium. Most motors are fitted with feet, or for direct mounting with flanges. The rotor and stator cores are basically compressed stacks of thin metal stampings, generally about 0.5 of a millimetre thick, called laminations. The function of these is to reduce unwanted eddy currents which would otherwise flow if the stack was made up from a solid mass. Without laminations, the motor would heat up unnecessarily and be very inefficient. The rotor assembly is complete with shaft, bearings and oil seals. This is a cage rotor. It gets its name from the way in which the aluminium end rings are bonded to bars cast into slots in the lamination stack. If we could remove the stack, we could see that the aluminium shape left behind would resemble a small cage. The remaining parts of the motor are its terminal box, connection board, and of course its label, which gives details of the supply to which it may be connected, its output in kilowatts, its speed, insulation type, and its IP classification, that is, the protection provided by its enclosure. This motor is the most common in industry and is known as totally enclosed fan ventilated, or TEFV. Motors are available with different types of enclosure to protect not only the motor, but the area in which it operates. For example, motors for use in hazardous locations, such as on an oil rig or a chemical plant, must be designed so that there's no possibility of arcs, sparks, and high surface temperatures. To find out a little bit more about how a modern electric motor is put together, I recently visited the works of one of Europe's largest producers at Honley in Yorkshire. This is the material that makes up the heart of an energy-efficient motor. This strip is polycore steel and has been specially developed to have low magnetic losses while having high permeability. That is, its ability to be magnetized and demagnetized easily. Very accurate dies enable the laminations for both the rotor and stator packs to be punched from the same strip in one operation. Stator laminations are assembled into correct size stacks and then welded on this semi-automatic machine using a process known as TIG welding. This excludes oxygen by introducing the inert gas argon. For some types of motor, the stator laminations are held tightly together by means of cleats.
We saw earlier that it is very important that the laminations are electrically insulated from each other to reduce eddy currents. This is achieved by soaking the stator and rotor packs in an inert atmosphere at a very high temperature. This process also anneals and de-stresses the stack. After a couple of hours in the oven, air is admitted, and although firmly secured together, a thin, even layer of insulating oxide is formed on both sides of each lamination. Slot insulators are made from a polyester-based material such as Nomex or Mylar, and are inserted into the stator by automatic machine. The stator coils are wound from high-grade copper, insulated with a special synthetic resin coating. This is flexible, tough, impervious to moisture, and resistant to aging. The coils are then drawn into the slots in one easy operation. This process ensures the best possible space factor, so that the maximum volume of copper is inserted into the slots, making the motor very efficient for its size. Although automatic machinery is mostly used on site, in order to build prototypes and motors of special design, it is sometimes necessary to insert the preformed coils using traditional skills. To provide additional protection from overheating in service, microtherms or thermistors, which are temperature-sensitive devices, can be embedded into the windings. To increase the electrical integrity of the motor, polyester phase barriers are placed between the windings. Insulating sleeves fitted to the coil ends, and excess wire trimmed off. After silicon rubber insulated lead-in wires have been fitted, the wire ends are gas welded together to form a strong, highly conductive joint, and the stack is ready for lacing and impregnation. Lacing is also carried out by a fully automatic machine, and this ensures that the windings are held firmly in place. At this stage, the stator is subjected to electrical tests to check the resistance of each winding and that phase rotation is correct. An insulation test is also applied. Before assembly, the windings are coated with a polyester varnish applied by a trickle process, the varnish being drawn into the windings by capillary action. Oven curing ensures that the windings are extremely rigid and largely impervious to contamination. Depending on the design of motor, the frame is either heated and shrunk onto the stator, or as an alternative manufacturing process, the wound stator pack is gently pressed into the frame. Before moving on to another operation, where the end plate registers are machined with great accuracy. This method ensures the minimum possible air gap between the rotor and stator, making the motor in service as quiet and efficient as possible. While the completed stator frame heads for the assembly line, we can see that the annealed rotor laminations have been fitted onto a mandrel, so that the rotor bars can be cast into the rotor pack slots using high purity aluminium. The bars and end rings are formed by high pressure die casting in a single operation. After cooling, the mandrel is driven out and the bore is burnished to a close tolerance to be a press fit onto the drive shaft. Most motor shafts have a milled keyway and a tapped hole in the drive end. Shafts are produced from high-grade steel bar using a computer-controlled machine which can produce single or multiple quantities of shafts with a simple change of program. The laminated rotor pack is heat shrunk onto the completed shaft by robot. Each rotor assembly is dynamically balanced. This is achieved by attaching small weights to the rotor in positions indicated by the machine. If a motor is to be vibration-free and have a long bearing life, a correctly balanced rotor is vital. All of the component parts have now come together for assembly. Once the motor has been completed, it can be moved onto the final testing station, where it is first subjected to an insulation test, then connected to the supply so that a series of dynamic tests may be made. These include running the motor off-load, checking that the phase currents are balanced, and that the no-load currents are according to specification. After testing, the motor is sprayed with a highly durable epoxy varnish, either by hand for small batches or in the automatic spraying booth. As a final stage, the fan cover is fitted and the motors carefully packed, either individually or in cases, to be delivered almost anywhere in the world.